So let me just remind that the group photo right after Nicolas stop. Nicolas Rugo is like undergraduate at Johns Hopkins University. Came here all the way from US. Nicolas will tell us about Nilpotent Quiver representation.
Hi. I want to thank the organizers, Professors Khovanov, Im, and Kim, and especially my two advisors for giving me the opportunity to work on this project over the fall. It's been very wonderful. So this is the archive number. If you want to read the paper, I'm only going to talk about section 3 of it, which is about linear algebra. There's also some set theoretic analogs of what I'm going to say. And my collaborators are Professors Im and Khovanov, and then also two other undergraduates, Wei-Si Chen and Catherine Lilia. So the structure of this talk is going to be some motivation for what I would like to prove. And then I'm going to talk a little bit about nilpotency for quiver representations. And I'm going to give you some definitions and notations for the case of your quiver being a two-cycle. I'm going to talk about what a balanced vector is, some results about balanced vectors, and we'll get to some enumerations in the case of finite fields. And then finally, I'm just going to give a short bit at the end, if I have time, about some further directions that I would like to go with our work today. So just some basic notations. Little k in cursive is going to be a field. Q is always a quiver. V is a vector space of dimension m. And W is a vector space of dimension n. Finally, n of V is going to be the null cone on V, which is just the nilpotent endomorphisms of V. Okay. So in section 1, again, I want to tell you about what we'd like to generalize for the two-cycle and what we have so far. So firstly, there's a very old result in algebra called the fitting lemma. It says that given an endomorphism, you can uniquely characterize it by two subspaces in V with three properties. The first property is that they're complementary. The second property is that your endomorphism is an automorphism of one of them, and it's a nilpotent of the other. That's the third property. So this uniquely characterizes all linear maps, and it's a key ingredient in the proof of this theorem of Tom Leinster. So all the way later in 2021, he gave a bijection. This is a bijection of sets of endomorphisms with the null cone times the vector space. And I want to warn you that most bijections, including this one that I'm going to present, are not canonical. This does depend on certain choices, although you can minimize them in a seemingly nice way. And the whole point of proving this was that you get a structural result that immediately specializes to an old result of Fine and Herstein in the 50s, which said that the number of points in the null cone on a finite field is this expression q to the m times n minus 1. Q is a prime power. So the moral of this process is that understanding nilpotency gives you some nice structural results that give you these kind of computation-heavy proofs without any computation. So the way you might prove this bijection is you'll form a subspace. It's called T bracket V. This is going to be the span of T powers of V, so V, TV, T squared V. This subspace has a canonical ordered basis. This ordered bases of subspaces are in non-canonical bijection with automorphisms of those subspaces. And then finally, you get a nilpotent on a complement of T bracket V, and voila, you apply fitting decomposition. If you notice this, there is a canonical way to choose the complement, so I'm not making an arbitrary choice here. I'm just not going to tell you how. Okay. So that's what we would like to prove in the next bit of this talk. So I'm going to use like kindergarten linear algebra, but otherwise I'm just going to assume known what a quiver is and what a representation is. So let M denote a representation of quiver Q. If you don't know what this is, it's a Q-shaped diagram of vector spaces and linear maps. And Q is just a graph. So Le Brun in 2001 gave this like definition plus theorem. We're going to call the representation of Q nilpotent if either one of these conditions is satisfied, they're equivalent. So either for any composable cycle in M, for example, this 3 cycle, the composite is nilpotent. Or a more conceptual definition would be to say that M is demanded to have a filtration of Q submodules or subrepresentations M1 through Mn, which is M. And we want the quotients to be these kind of simple, very basic representations where we have the ground field K in one vertex of Q, and then everything else is 0. All the maps are 0, all the vertices are 0. If you think about it, you can recover the original definition of a nilpotent matrix or linear operator by just taking Q equals the 1 cycle. And then you'll see that we get what we wanted. Okay. So we are going to call, we're now going to fix Q equals C2, which is this upgrade of C1. And most of the time I'm going to consider fixed support being the underlying vector spaces on the vertices. So again, I'm going to stick with a dimension M space V and a dimension N space W. So some points of notation before I state results. First of all, N of V comma W is going to be this like double nilpotent cone. So it's going to be the nilpotent representations of C2 with support V and W, which again is pairs of linear maps from V to W going both ways such that one composite is nilpotent. If one composite is nilpotent, then the other one is. And again, just all representations is just Hom VW times Hom WV. So given a nilpotent pair, which is an element of here, I get 2 endomorphisms by composing in either direction. I'm going to call the one on V T, and I'm going to call the one on W T prime. Okay. So now we have enough to state the first important definition. So pick a vector in V, or you could do it in W. It doesn't matter. There are 2 cases. Either the dimension of T bracket V, which is the dimension of span of the powers of T acting on V, equals the other side, T prime bracket FV, which is the span of the T prime powers on FV. In this case, we say V is balanced. Or we get the bad case, which is where this has one dimension higher than this. If you want an example, V is a non-zero element of the kernel F. Or you can take some vector such that a high enough power is a non-zero element of the kernel of F. Any questions? Okay. So I can now tell you results. So the first thing is this fitting style decomposition. Any C2 representation is determined by subspaces. You get 2 in V, Vi and Vn, and you have 2 subspaces of W, Wi and Wn. And the idea is that the representations are characterized by these properties. So we're going to demand that the subspaces be complementary, just like before. And we're going to demand that F and G respect this decomposition in the following way. So we're going to say that F carries, I should write VI, Vn, Wi, Wn, and vice versa, Wi, Wn, Vi, Vn. So we're going to demand that F has this block diagonal form, and S1 and S2 are going to be isomorphisms. And N1 and N2, well, there's no notion of nilpotent for a map going in one direction, but we're going to demand that they compose to nilpotents. That ends up being good enough. So the first theorem that I have for you is that we have a bijection of sets, again, it's non-canonical, of triplets with linear map F, linear map G, and vector V, such that F and G form a nilpotent pair, and the little v in V is balanced. This is a non-canonical bijection with Hom VW times Hom WV. So I have figured out how to get any representation of C2 with V and W as its support as some kind of nilpotent plus extra data, much as like the original fitting lemma. So again, or as Leinster's theorem, excuse me. So again, the idea is to reduce to fitting when you prove this. So you'll have two subspaces, and you need to apply the original fitting lemma to T and T prime. That's these T and T primes. You get your subspace decomposition. And then it's a matter of just checking that F and G actually do satisfy these things. So one issue with this theorem is that it's not quite enough to say anything enumerative, because I kind of have V inside, and the number of balanced vectors for a pair depends on that pair, so I'm not quite ready to count yet. So to amend this property, we'll say some more. Okay. So lemma. Here's another bijection. Where again, F and G are nilpotent, and VB and V, WB and W are balanced. Like I said before, we can always have balanced vectors in W. It's a symmetric definition. This set is bijective with, sorry, this is not 0. VB cannot be 0. This is bijective with nilpotent pairs plus two unbalanced vectors in either space. So this lemma is telling me that I have a canonical way of passing between balanced and unbalanced vectors. This relies on a particular observation that given a balanced vector, its pre-image is unbalanced. Given an unbalanced vector, its pre-image is balanced. So I have a way of flip-flopping. I'll give you a little proof by picture. So here's my V, there's my W. I have VB, I have FVB, and I have F or GWB and WB. So since FVB is the image of a balanced vector, FVB is unbalanced. Since GWB is the image of a balanced vector, it's unbalanced. I still have F and G acting like this. What you first show is that these spaces are orthogonal. They only meet at 0. That's because a balanced vector and an unbalanced vector do not exist in the same span. Once you've done that, you're going to define, let me call this set A, let me call this set B, an element so I'm going to call it F prime, not going to do anything to G, not going to do anything to VB, and I'm going to take the image of VB as my unbalanced vector in W. Okay, how is F defined? F prime equals F on V minus span of VB union 0. So on any complement of span VB, and then F prime of VB equals WB. So I've kind of taken this vector and stuck it over here, whereas F was taking it here. The reason why we do this is because, well, first of all, it's a reversible process, but this forces VB to now be an unbalanced vector. This makes FVB also unbalanced, and it doesn't change the nilpotency. And that's why we have a bijection like this. How much time do I have? Okay. All right, so the moral of this story is that using this lemma, I can make some formal manipulations with things to get this theorem. There exists a bijection. We're going to do HOM VW times HOM of WV times V disjoint or union along 0W. So that's like if this is V and this is W, then it's their union but not their sum. This is in bijection with N of VW times V times W. So corollary. I'll say it in the cute way. Probability that A, B in the probability of a pair of matrices with both products defined has BA nilpotent. Again, we're working over a finite field. We can count things. Is q to the minus m plus q to the minus n plus, sorry, this is a minus, q to the minus m minus n. And this is immediate from this. So again, I have counted for you points on the null cone of this quiver without doing any combinatorics, much in the same way that Tom Leinster does it for one cycle. So very briefly, I'll mention one of the directions that I think this could go in. So Guzman and, I hope I'm saying this right, Reinecke showed that the Fine-Hurstein theorem about counting nilpotent matrices lifts to a calculation of, I'll call it the equivalence class of the null cone of V in K0 of complex varieties. So what Fine-Hurstein actually did is they calculated the motives of this null cone. So one of the things I'd like to do moving forward is to lift this result to a description of the motives of this binilpotent cone. Do I have any time left?
Yeah, a couple of minutes.
Okay, great. So yeah, what we would suspect is that their result is that this equals a1 to the m times m minus 1, where again m is dimension of V. We might like to see, they gave a different formula for this, but it was based on quite a lot of recursion and counting. What we would like to see is that the null cone of V and W is a1 to the 2mn minus m minus n times a1 to the m plus a1 to the n minus 1, where 1 is spec C. So finally, here's direction 2. So in 2021, Griffin, Levinson, and Wu constructed varieties Y. They're parametrized by natural numbers n, partitions lambda, where lambda is a partition of k, which is less than or equal to n, and then some number s, which I'm just going to say is bigger than or equal to, bigger than the length of lambda, length being the number of rows in its Young tableau. So these guys constructed varieties y and lambda s such that you get a Springer-like correspondence for their cohomology, but instead you get induced modules instead of the usual spec modules. So what do I mean by that? Top degree cohomology of y and lambda s with q coefficients is isomorphic as modules to ind s n minus sk times s n minus k up to sn of spec of lambda, the spec module associated to this partition. If you're worried about how this acts here, this part is acting trivially, and this part is doing the action. So the second conjecture I'd like to throw out to the audience is, does the resolution of n of VWs singularities give the representation theory of a group G in cohomology a la Springer? I suspect the answer is yes. That is the topic of future work. The last direction is to replicate all of the results of this paper for the K cycle, CK. The reason this is hard is not obvious, but what it ends up being is that you can't get this anymore to get your enumerative results, because no longer do you have the nice property that the preimage of unbalanced vectors is balanced. You might have to take many preimages of an unbalanced vector to get a balanced vector, because you have to go around and there's a lot of places it could be in the kernel of. Exactly. And that is all I have to say.